Today on lesson 2.6, and we're going to now move into working with compound inequalities. So we were working with what are called simple inequalities before, which you just tested on. And now we're going to move into, let's combine simple inequalities. So when two simple inequalities are combined into one statement, the result is called a compound. So two of them are put together into one, then we call it a compound inequality. So compound inequality. So when you were working on that warm-up worksheet for today, you actually had situations where you had to combine two things. You had to think about both of them at the same time. So sometimes you had to decide if both things were true, and because they used the word and. And then there were other times they used the word or, and just only one of them had to be true for you to be able to say that the two of them combined together with the or between them was true. So there's two types when we're working with these algebraically. We have the and, so just like you had in the work for today, an and one is called, what we're looking for there is an intersection. In other words, for it to be true, it has to make both parts true. It has to make both simple inequalities true. Just like in your statements for today, it had to make both of them true, or you couldn't say that P and Q was true. So we call that an intersection. When we graph these, when we try to find the region, or that is the solution region, it typically is between our two endpoints. So that the overlap, the solutions that belong to both of them typically fall between the two endpoints. Well, then the other type of compound inequality we have is the or one. And the or one is what we call a union. Or in other words, we put them both together and say, you know what, our compound inequality, our solution only has to satisfy one or the other. So we can union them together, we can combine them together. So even if one is true and the other one is false in your statements for today, you said P or Q is still true because it met one of the standards. It didn't have to meet both of them. Typically, when we graph these, the solution region is going to be opposite the endpoints. So it's going to go out opposite directions from those two endpoints. So let's just start learning, take a look at what they look like and start solving them. Let's first of all, would you circle here so that you can really draw to your attention? We're going to start with the and compound inequalities. And when we solve these and compound inequalities, we're going to do the same thing to all three regions. There will be three regions in the inequality. We've been working with simple inequalities where there's only two sides. There's what we could call two regions. We're now going to add in a third region here when it's an and compound inequality. And the x term will be in the middle region. So we got to get that x alone. It can't have anything being added or subtracted from it. It can't be getting multiplied by anything. It can't be getting divided by anything. We want a 1x. Okay, so here's an example of our an and compound inequality. -5 is less than x plus 1 is less than 2. So basically what they're saying is x plus 1 in the middle has to be, if I read that from the inside out, if I start on the inside, I have x plus 1 is greater than -5, and it's less than 2. So it has to satisfy both of those. So we're going to start by, what do we have to do in the middle to get that x alone? So we look in the middle and we see we need to subtract 1. Well, if we subtract 1 in the middle, we have to go do it over on the left, and we have to go do it in the right. We have to do it in all three regions. So -5. Take away 1. That's the same as negative 5 plus a negative 1. So 5 below 0 goes down another degree, just like our cold temperatures right now. It's negative 6 now. Is less than, x is now by itself in the middle region, and is less than 2 take away 1, 1. So we call this the algebraic solution. So let's put a circle around that, or let's show it as our answer for it algebraically. And then let's go see how would you graph that. So now our graphs are going to change a little bit. You know how we have one endpoint, and then we've been doing the neighbor to the left, the neighbor to the right, the integer neighbors on either side of our endpoint. Now what we're going to do is we're going to put 2 tick marks, and we're not going to worry about distance because those are the only 2 numbers that are going to be labeled on our number line, negative 6 and 1. Negative 6 is to the left of 1 on the number line, so we have to put it where it belongs. What this says, let's write this down right here. This is what this really says. This says, we're going to read it from the inside out. X must be greater than negative 6. Did you get caught up there getting that written down? This says x must be greater than negative 6. So negative 6 is not included. So we're going to put an open circle at negative 6. And what are the numbers that are greater than negative 6? To the left or to the right? Well, those are going to be these guys going this way. So we're just going to kind of make that little scribbling there for a little bit. And now we're going to go back to our compound inequality that this says x must be greater than negative 6, and so it has to meet both situations. It has to be greater than negative 6 and less than 1. And less than 1. So we only want the numbers that meet both of these standards. So we already decided that negative 6 is not included. The numbers to the right of it would be, but then once we put in that other condition, and less than 1, now we're going to go and put an open circle at 1 because 1's not included. It has to be less than 1. And the numbers to the left of 1 would be included. But we have to stop when we get to that negative 6 because remember, it also has to be greater than negative 6. So only those numbers between negative 6 and positive 1 qualify as being solutions. So there's our graph showing our solution set. So we have our algebraic inequality and our graph showing it. Okay, let's do another and one here. Number 2. We're going to, again, we're going to look at that region in the middle where the x is, and we're going to say, what would I have to do first? It's 3x minus 1 in the middle. So that's where our focus goes. We look at this right here in the middle and say, what do I have to do? Well, our first move would be to add 1, to get that 1 out of there. If we do that there, we have to go do it in the region to the left. We have to go do it to the region on the right. So now we have 8 plus 1, which is 9, is less than. 3x is now alone. We've gotten rid of the 1. Is less than or equal to 11 plus 1, 12. Okay. Well, it's not just x in the middle, it is 3x. So we look at that and say, what do I have to do to get x alone? I have to divide by 3. If I do that there, I have to do it on the region to the left. I have to do it in the region to the right. All 3 regions have to be divided by that 3. So let's see, what's 9 divided by 3? 3. Got lots of 3's going on here. Is less than. These 3's cancel. X is now by itself. Is less than or equal to 12 divided by 3, 4. There's our algebraic representation of the solution to this compound inequality. Okay, so this is where we're going to graph it. Remember, now we only need, for these compound ones, we just need the two endpoints, 3 and 4. Let's go see what this says. Let's write that again. This says, reading it from the inside out, x, this says x must be greater than 3 x must be greater than 3 and, because it's in the middle between the two of them, and less than or equal to that 4. X must be greater than 3 and less than or equal to 4. So we have to find the numbers that satisfy both of those conditions. We need numbers greater than 3, so 3 can't be included, and less than or equal to 4. 4 can be included. So where are those numbers that are greater than 3 and at the same time they're less than 4? Greater than 3 and less than 4 looks like all these numbers in between. So 3 is not included, anything bigger than 3 is, and then 4 is included, and anything less than 4 is, and nothing outside of that region would be in our solution set. So there's our solution set represented with a graph. Okay, so those are our and ones. Let's go to the back side, where we'll work with the other type, the or compound inequalities. So let's circle that word or so we know that that's what we're doing when we see these examples. We're going to, when we have the or ones, they're actually written as two separate inequalities with the word or in between them. So we're going to solve each of them separately. So this is going to look familiar. Solve each of them separately and then combine, put together, just make one graph. Combine their solutions on the graph. So we're just going to have one number line, even though we have two simple inequalities with the word or in between them. So they're like in number 3, there's our first one. It has an or in between it. So we have 2x plus x, or 2 plus x is less than 12. There's one in simple inequality. Or x minus 5 is greater than or equal to 9. So again, we're going to solve them separately. So let's work with the 2 plus x is less than 12. We need to get that 2 out of there, so we will subtract 2. And we're going to have x alone is less than 10. But let's bring down the word or so we don't forget that this is an or. And then now let's deal with the other one where it says x minus 5 is greater than or equal to 9. We're going to add 5. And we're going to have the solution for that one. X is greater than or equal to 9 plus 5, 14. So there's our solution. I'm going to box that because it had that circle around the or there. X is less than 10, or x can be greater than or equal to 14. It can be one or the other. So we have a couple of situations here that get to qualify. So we're going to make our number line. We're going to do the same thing we did with the and ones. We're going to have two endpoints. 10 comes before 14 on the number line. And let's graph the first one. It says x is less than 10 because remember, x gets to be from this region. So x is less than 10. That's 10 is not included, but all these numbers going this way are, or x can also come from the region that says x is greater than or equal to 14. So 14 is included, and all these numbers greater than 14 are going to the right of 14 on the number line are also included. So there's really This is where I talked about how it would go opposite from the endpoints. Typically, this is what the graph looks like for an OR. Okay, let's try number 4 here. Remember again, when the word OR is in there, we're going to solve each of them separate from this. So whatever it takes to solve the one that you're working with, and then you go over to the other one and it's got its own thing you probably need to do to it. So we're going to take 7x and we're going to divide by 7 because it's the x we want alone. And now we have our solution just like that. X is greater than or equal to 21 divided by 7, 3. Bring down the word OR. That's because this is a compound inequality solution also. And then we're going to solve this other one, which is going to say, you know what, you should divide both sides by 2 to get x alone in this one. And now we're going to have x is less than, we divided by positive in both of these, so notice we didn't have to switch the symbol. And x is less than or equal to -1. So there's our, again, algebraic solution. That's how we represent it algebraically. And now we want to show it on a number line. Our endpoints are 3 and -1. Which one comes first on the number line? Not the 3, the -1 does. So we have to be careful. Just because the 3 is in the first part doesn't make it first on the number line. So let's go deal with the first one here that says x is greater than or equal to 3. So we're going to go to 3, 3's included, and the numbers to the right of it, greater than 3, are included. Or x can come from the other region, which says x is less than or equal to -1. -1 is included, and the numbers going this direction are also included. So there's our graph representation of the solution to that compound inequality. Okay, we'll practice one more. We have, again, an OR one. So we're going to solve them separate from each other. So we're going to, we have 3x minus 2 is less than 7. We're going to deal with that subtracting 2 first. Undo it by adding 2 to both sides. We now have 3x is less than 9. Divide both sides by 3. And we have x is less than 3. Remember, we can't forget to bring down that word OR. And now we'll go solve our other one. X minus 8, we just need to add 8 to both sides. And x is by itself right away. X is greater than -1 plus 8. That is positive 7. But that's up higher than the other one, so I'm going to bring it down here to combine it with the other part of the solution. So our compound inequality solution is x is less than 3 or x is greater than 7. So we're going to make our number line with our endpoints. 3 comes before 7 on the number line. X is less than 3. 3 is not included, but the numbers to the left of it are the ones that are smaller than it, that are less than it. Or x can come from this region. X is greater than 7. 7's not included, but all these guys to the right are. So there's our graph representation of the solution. Okay, this is what you'll be working on today in your homework, and I'll see you tomorrow.